Okay, notes 2.6, the product and quotient rule. So now that we learned those basics of the derivatives, those derivative rules, now we're going to look at two new things, and that is the product rule and the quotient rule. Well, the product rule says that if we are multiplying two functions, that is the same as taking the derivative of the first function times the second function plus the first function times the derivative of the second function. I like to write this as f prime g plus fg prime to help me memorize it easier than having to remember all of the x parts. Okay, so let's look at an example. So here is our function here. Notice that this is our first function f, and this is our second function g, and I wrote them off to the side over here. From each of these, I take the derivative. Well, the derivative of 2x minus 1 is 2, and the derivative of x minus 4 is 1. So using my formula here, f prime, which is 2, times g, which is x minus 4, plus f, which is 2x minus 1, times g prime, which is 1. And then I just simplified by distributing the 2, distributing the 1, and then combining like terms to get my answer of 4x minus 9. More examples if you want to try these on your own, see if you get the same answer. Okay, then we have the quotient rule. So the quotient rule is similar to the product rule, okay? So notice here it says if we have two functions that are being divided, we could do almost the same as the product rule, but subtract them and then divide by g of x squared. Again, I like to memorize this exactly like I memorized the product rule. So f prime g minus fg prime all over g squared. That way you only need to memorize this portion for both the product rule and the quotient rule, and know that for the product rule it's plus, and for the quotient rule it's minus, and then the quotient rule is also being divided by g squared. Okay, so let's look at an example. Okay, so in this example, we have two functions being divided. The top function is f, the bottom function is g. We then take the derivative of each. So the derivative of f is 6x squared plus 8x, and the derivative of g is 1. And then I write g squared off at the bottom, just so I have everything off to the side in order to plug it all into my formula. So then I plug everything in. Here's f prime, here's g, minus f times g prime. Well, technically g prime is 1, so I could have wrote times 1 off to the side, but I don't have to. And then I divide everything by g squared, which is x minus 5 squared. There's no need to simplify this. I would just leave it as is, because remember, we are checking your calculus skills, not your algebra skills. And then same thing, I would go through each of these and make sure you are able to get the same answers. Okay, let's see. Okay, more trig functions to memorize the derivatives. So we already know that the derivative of sine is cosine, and the derivative of cosine is negative sine, and the derivative of tangent is secant squared. We learned those in the previous notes. Now we have the derivative of cosecant, which is negative cosecant times cotangent, and the derivative of secant, which is secant times tangent, and then the derivative of cotangent, which is negative cosecant squared. Again, I would just memorize those when we are asked to actually take the derivative of those type of trig functions in a problem. Okay. Another big thing here, it says higher order derivatives. So this is now taking you from calculus to physics. So it says S of t is the position function. Velocity is the derivative of S of t. And acceleration is the derivative of velocity, or in other words, the second derivative of the position function. So this is talking about higher order derivatives, which means we can not only take the derivative one time, but we can take the derivative 2, 3, 4, 5 times, as many times as necessary. Okay. This would be the notation for taking the derivative 1, 2, 3, 4 times in all the different forms. Remember, we learned about all the different types of ways we could write derivative notation. Okay, so let's see. So for example, let's look at B. So B wants us to find the fifth derivative of f. So here's f. So I would first find the derivative of f. So here's that derivative. Then from that first derivative, I can find the second derivative by just taking the derivative above. Then I can find the third derivative by taking the derivative above. I can find the fourth derivative by taking the derivative above. And then I can take the fifth derivative because I know that the derivative of a constant is always 0. So notice, as I keep going, I'm eventually going to have to stop because eventually I will get to 0. So this is not saying that every function has unlimited derivatives. There is a certain amount of derivatives that it would take to get to 0. And since in our example here, our leading exponent, so our highest degree is 4, which tells me I'm going to take 5 derivatives to get to 0. If it was 6, I would take 7 derivatives to get to 0. Okay, some more examples to look at. This would be a special case here because we know that sine, the derivative of that is cosine, but the derivative of that is negative sine. So this is one of those where we're not necessarily going to ever reach 0 because we're just going to go back and forth in a pattern. Okay, so some examples here. If you want to look over them, make sure you know how to do them all. And that is the end of note 6.